So one of the homework problem was to calculate the spin density plot for CH2CHR. And let us open the output file what we have already run. So this is my terminal carbon, maybe the picture would make it easier. These are my terminal carbon. So this one I write as terminal T, this is my substituent carbon, and this is in this nomenclature what is called a central C. And if I go to the spin population analysis, the terminal carbon has a analysis of 0.994, the central carbon has minus 0.74. By mistake I have written the substituent carbon as 85, it will be also 0.99, which makes sense because if you see the structure, this is quite symmetrical. So it's likely that the spin density at these two carbons, the terminal one and the substituent one, will be similar. If we visualize the spin density cube which we have already generated, I can open it with Chemcraft. Showing very small, so maybe I can change the contour value. As you see, the spin density plots are actually quite similar, and if you look at the sign here, the sign of the plus slopes are marked in orange and the minus is marked in blue. Maybe I would go for the best view. This is how I wanted to see it. Now let us do with sulfur substituent, and subsequently we will do for beryllium. So to do for the sulfur substituent, what I need to do is I delete both the hydrogens here. I replace this one with a sulfur, and I don't need to adjust the hydrogen. And I will do a quick optimization, and then I will generate the, it should be 0 to RHF F to SVP. This is fine. Let me write it as allyl S. I have written, let me check the name again. I think S is capital. Okay, the picture I have made, I can save the picture, save image. When you have make the image, you can actually make the background transparent. No, I want to go to the NPTEL folder only. can put this picture here. Insert picture, this device. My calculation is done. In the previous case, we have seen a symmetry in the spin density. Here, if you see the spin density at the sulfur point has increased. So, if you want to say which number is which one, I could open the output file with ChemCraft just to check the numbering. So, 4 is my terminal carbon, 2 is the central carbon, and 1 is the sulfur. So, by this nomenclature, if I now go back to my output file, so my terminal carbon now which is now 3. So, remember the counting start from 0. So, 0 is sulfur, in this case it is 1, maybe I try to shorten it a little bit. Now you can see. So, this is sulfur, this is, in this case this one is positive and this one has acquired a negative charge, and now you see that this positive charge and this negative charge is actually quite different. If I open the previous one, you could have seen that both the terminal and the substituent carbon has similar charge. So, let us now put it one by one. So, this is +1. Okay, I can make only up to the significant digit. So, this will be 0.48, this will be 0.16 and this is 1.152. Remember, this will be negative. So, if I want to generate the cube file, I should use ORCA plot. To check the GBW file name, why it's not showing the GBW file. Small l is missing. So, enter the type of the plot. I want spin density, so it's number 3. I need the select of the output file. In this case, it's Gaussian cube, that is 7. Now I need to only generate the plot. So the plot is generated. I exit the program. So this spin density cube file is generated. Now I'll open it with Chemcraft. Now you see the asymmetry. So because this part is positively charged, now this is, and it is orange, and this is now blue, the negatively charged one, the terminal one. So let's save it as image. This is LIS. Again missing the small l. So if I now put it this picture here so that we can make a visual comparison also. Now the only one left is the beryllium one. So what I can do here is that I can replace my this length should have been increased, but it's okay. First of all, let me save it in case it gives me a problem later. Okay, now let me try to make the Orca input file. So it has been saved. Let me run the calculation. So it's done now. Let's open it. You see the substituent has slightly smaller charge than before. I can keep it up to 0, 1. This must be my central carbon. And my terminal carbon is -3.0. because we could have opened it with the chemcraft. This 1 to 4. We are good. Now we need to generate the GBW file to plot it. So it's OTCA plot. Again, I have not used the L. Type of plot, I think it has to be 3. That is SCF spin density. Yes. And then I go to select the output file. My format will be Gaussian cube. I will generate the plot. I will exit the program. So now I will open the spin density plot with chemcraft. I think I should close. I think I have too many chemcraft open. Now I should open it. So here you see it's slightly more symmetric than what you see. That you can see from the magnitude also, because the positive and the negative charges are almost similar in magnitude, where in the case of sulfur it was more asymmetric. So let us now save this picture. Let us go to, this is the key for the best view. Oh, maybe I have to rotate a little bit. Add this one here. So let me keep this format only. Save image. Okay, this I should make it to write significant digits. This should be 2, 8, and let me insert the picture. So here they look like. The next homework problem was to calculate the low spin state of Li2. So to do that, we have the input file, and we have discussed that you can actually do the spin flipping in multiple ways. So it's Li spin flip dot inp. So it's SCF, it will flip the spin, final MS will be 0. So I'm looking for broken cell singlet, and I will start with the triplet geometry. So everything looks fine for the time being. Volca. There is some formatting errors. We can fix it up quickly. Now it's running, I believe. Let us look at the output file very carefully. This is the input file. So first what it is doing is it's actually doing the calculation for the triplet state. This is the triplet energy. And you can see from the expectation value of the square operator that is actually a triplet. Now it's flipping the spin on atom 1 to make it an open shell singlet. I just copied the triplet energy back into the output file, and now my number of unpaired electron is 2, among which my number of spin up electron is 4, number of spin down electron is 2, so homo spin up is 3 after. So this was my contribution before I flipped the spin. So before the spin my multiplicity was 3, number of unpaired electron was 2, both of them were unpaired. So number of up electron was 4, number of down electron was 2. So the resultant homo spin, the resultant 2 electrons were up, and after the flipping of the spin is multiplicity is 1, there is no unpaired electron, the number of spin up electron is 3, number of spin down electron is 3, and after I did the calculation, this is my broken symmetry energy. And from the square value you can see that this is actually a contaminated calculation. And the energy of the open shell singlet is lower than the triplet. Now let us calculate for the same one, let us calculate the energy of the closed shell singlet. That is actually very straightforward. It's Li singlet dot INP. I really do not need any of this keyword, and the multiplicity should be made 1. And let me save it and run it the calculation again. So my calculation is done. This is the singlet output file. My energy total charge is 0, multiplicity 1. This is my total SCF energy. You can see this is much higher than both triplet and open shell singlet. And because it's a closed shell calculation, so we have not calculated the expectation value of the square operator. you could have used an UHF reference to do that. And now you can see in energy ordering, the closed shell singlet is actually much higher in energy than the triplet or the open shell singlet. Open shell singlet has the lowest energy in this case. So, in the next class, we are going to discuss much more about basis set. We have came to know about SCF, we are going to know more about basis sets. And then we will see how to do from that.